So we have talked about electric force and electric field, and let's review that before we go on and talk about another term that is sometimes confusing, and that is electric potential. So first of all, let's just do a quick review of what we know so far. First of all, we know that if we have two charges, Q1 and Q2, and that they're separated by distance r, that the force, assuming that these two in this scenario are the same charge, will be equal and opposite on each one, and the size of that force is found by finding the electrostatic force, or Coulomb's force, which is K times Q1 times Q2 all over the distance squared. And that would just be the absolute value of that number. And K is equal to 8.99 e to the 9 newtons meters squared all over Coulomb squared. So these charges, if they're the opposite charges, the force would have a negative value and they would be repulsive. If they're the same polarity, then there'll be a positive value, which indicates repulsion. But the value of the force on each one is equal and opposite, and its magnitude is found using this equation, Coulomb's law. We also talked about the fact that charges have an electric field around them because they exert forces on other charges. And that field is there whether or not another charge is near them. So, for example, if we have a positive charge, Q, right here, and we bring some test charge near it, right? We'll call that Q naught. It's going to experience a force. And if they're the same charge, and our test charge is always assumed to be positive, because when it was first considered and thought up of, it's before we even knew that there were electrons. And so you either had electricity or you didn't, according to Ben Franklin. And so positive charge meant that you had some kind of this electric, fluid in you. So this positive test charge, Q naught, if we place it right here, a distance r from our charge, then it's going to feel a force of repulsion. And even if we don't have Q naught there, it is going to feel a force of repulsion, Fe. And we can find that force in newtons using Coulomb's law. And that force is always going to be a force of repulsion. So even if there is no charge there, at any location, a distance r, that same distance, at any location around that charge, it's going to feel that force, right? And that force is going to be exerted on any positive charge that goes there. Now, it will be different if it's a different amount of charge, right? So we have to have some way to quantify that, and we call that the electric field. And we describe the electric field as being as pointing in the direction of the electrostatic force on a positive charge at that location. So away in this case from the source charge, big Q. And it is really how many newtons every coulomb of charge will feel at that location. And it turns out that if we find that equation, it's equal to whatever the electrostatic force is divided by the charge at that location. And if you plug into Coulomb's law, that factors out Q naught, K, big Q, all over R squared. So that means that it doesn't depend on there being a charge there, that there is an electric field there. And for positive charges, the electric field points away, and we can draw these field lines that illustrate that. So if I put a positive charge anywhere in this field, like say right here, Q naught, it's going to feel a force pointing away from it, and it will move in the direction of the electric field line. The closer the lines are, the stronger the field. The further apart they are, the weaker. So the further you go away from that point charge, the weaker the field is, doesn't exert as much force because Coulomb's force is inversely related to R squared. So Our next term is going to be electric potential energy. So let's talk a little bit about that. And we'll go back to electric potential energy. And let's review what we know about gravitational potential energy. So let me just see if I can add a page right here. Okay, we'll just do it right here on this page right here. All right, so what do we know about gravitational potential energy? So if we have the Earth here, the mass of the Earth, and we have somebody holding a ball, mass of the ball, that if that ball is a certain distance above the surface or above the Earth, that its natural tendency is that if we let go of it, it wants to fall down because there is a gravitational field around the Earth that points down towards the Earth, right? And that gravitational field, we measure it as the acceleration of gravity. And gravitational field is equal to the ratio of the weight to the mass at that location. And at this particular location is the mass of the ball, right? Is a ball. And we know that if we let go of the ball, it's going to follow that field line and go straight down and fall. What we also know is that as it gets closer to the Earth, this force gets bigger, right? And if it gets bigger, then the field is stronger as you get closer to the center of the Earth. We also know that that it picks up speed. So according to conservation of energy, you can't just all of a sudden have more speed. It has to come from somewhere. You don't just all of a sudden develop kinetic energy. It doesn't just come from nowhere. It has to come from somewhere. So there must be a certain amount of stored potential energy at that point, at that location. And that stored potential energy is gravitational potential energy. The symbol for it is U. And it's equal to the force that's acting on the ball, which is weight, times the distance that it falls, R. And if we substitute in the formula for weight, we get mg over r. So as the mass falls, r gets smaller, and that makes ug get smaller as well because it's a direct relationship. So as it falls, it loses potential energy, but it gains kinetic energy. So it gets faster. So the rule of thumb is that when a mass moves in the direction of the gravitational field line, it increases its potential, it decreases its potential energy, and it increases kinetic energy. And if we lift the ball up, we're moving against the field lines, which means that R is getting bigger, UG is getting bigger, but it will lose whatever potential energy it gains. So if we throw it up in the air and it rises 100 meters, it gains a certain amount of potential energy, but it slows down, right? So whatever energy it gains is the kinetic energy it lost, conservation of energy. So how does that relate to a charge in an electric field? Well, here's our charge, positive charge. And we're going to put our test charge in here. And we're going to draw our field lines. Always, oops, my bad. Always pointing away from the positive charge and towards the negative charge. So if I put this positive test charge in here, it is going to want to move away from the source charge because it's repulsed. And it's going to move in the direction of the field line. And as it does, we're going to use that same rule. If it moves in the direction of the field line, it's going to lose potential energy, but gain kinetic energy. It's going to lose potential energy, but it's going to gain speed. Lose potential energy and gain speed. So we can calculate the potential energy at that point by the same way that we did the other one. Potential energy, and this is going to be electric potential energy, is going to be equal to the force that's acting on it, which is Fe, times the distance that it moves, r. And if we put this in our formula, we're going to get Fe is K, big Q, times Q naught, all over r squared times r. So UE is either going to be, it's going to be K, big Q, all over r, okay? Or it's going to be Fe times r, either way. But the point is that this point has a certain amount of electric potential energy. And if Q naught moves in the direction of the electric field, it will lose UE, but it will gain K, kinetic energy. Now, it's a little tricky though, because the force is not constant along this line, right? Force is inversely related to R. So as it goes away from it, it's going to have less and less force on it because the electrostatic force decreases with distance. So it's not going to, it's not exactly the same as what's going on in the gravitational field, but it's similar. But when it's closer to that source charge, it's going to feel the most force, and it's going to have the most potential energy. All right. Now, if we were to try to move Q naught the other way, if we tried to move it this way against a field, it's going to do the exact opposite, right? It's going to gain potential energy because this force is going up. And it's going to lose kinetic energy because its natural tendency is that it does not want to move in the field. So what if we have a negative source charge? So if we have a negative source charge, right, and we put that positive test charge in there, the field lines point towards the negative, right? Because that positive charge is going to be attracted. It's going to be attracted to the negative charge. So when Q naught moves in the direction of the field line, it's still going to lose potential energy because it's going to speed up. If it's speeding up, then it loses potential energy, but it's gaining kinetic energy because of conservation of energy. So electric potential energy is going to be measured in joules. And once again, it is related to how much force is acting on it through that distance, how much work that force is doing on it. And if a charge moves in the direction of the field, it's going to lose potential energy, but gain kinetic energy. And if it moves against the direction of the field, it's going to gain potential energy and lose kinetic energy. So just like we have electric force and electric field, which exists around that charge, we have something else that's similar. So remember when we talked about electric force, it's measured in newtons. And electric field is measured in newtons per coulomb. And it is something that exists whether there's a charge at that location or not around another charged particle. we now have electric potential energy, which is measured in joules. We're going to have a similar quantity that's going to tell us how much potential energy